All right, today we're talking about Chapter 7, Section 1. But before we begin, I want to show you how we navigate this in MyLab Math. All right, so once you land on the home page, one moment. Okay, good. Just make sure my voice is recording. All right, so once we land on the course home page, you're going to go to Assignments. Okay, and as I said, today is 7-1. The e-text is a little hard to navigate. Okay. Because the chapters aren't necessarily labeled. So what we would do is we're going to go here to 7.1 lecture, inductive and deductive reasoning. All right, and you're gonna go through all these. I believe this is a PowerPoint. You click on it and you download the PowerPoint. Check out the PowerPoint. You also have, this is the actual textbook, okay, but we're not going to click on that just yet. But for supplemental material, if you need to, here are videos that you can click on, short little videos. This is a minute. She's talking about inductive reasoning, maybe, I don't know. But these are different little videos, and then same thing down here. These are just little videos to watch to kind of supplement your education here, right? This is only 5 minutes long, but I will say that, I mean, you really could just sit there and watch the lecture and be done with it, but I do suggest that you do check those out. But the main thing I want to point out here is this textbook, okay? It's a little textbook icon, and so you're going to click on that, and it's going to take you to the textbook. It's going to take you exactly where you need to be. There it is. So today we'll be talking about inductive and deductive reasoning. One moment. Put this in tablet mode. Alrighty. So in this particular class, what we're going to do is we're going to basically read the textbook when possible. Okay. The main reason why is because, shoot, I don't know if I said this in the syllabus day or not, but I'm gonna repeat it if I did. The best and worst professor I've had in my life was my chemistry professor, and they were so bad that I actually had to go home and read the textbook. Okay, that's the worst part of the professor, right? The best part was that since I had to go home and teach myself, I became a chemistry genius because I actually opened up the textbook. So I like to teach from the textbook and actually show the textbook and all that good stuff because, well, that's where all the information comes from. Alrighty. One thing that does kind of drive me a little crazy is, you know, literally reading the textbook in front of you. So I will do that in some cases, but in some cases I would just leave it up to you to read it. And this first page is one of the main things, right? So up here, I think it's interesting. It's very interesting. You should check it out. But I'm not going to read it to you. Instead, we're going to come down here to mathematics in your life. Right? So a major goal of this text is to show you how mathematics can be applied to your life in interesting, enjoyable, and meaningful ways. The ability to think mathematically and reason with quantitative issues will help you so that you can order and arrange your world by using sets to sort and classify information, use logic to evaluate the arguments of others and become a more effective advocate for your own beliefs, understand the relationship between cutting-edge technology and ancient systems of number representation. Try to flip the page here. Understand the mathematical paradoxes of voting in a democracy, increasing your ability to function as a more fully aware citizen, and use graph theory to examine how mathematics is used to solve problems in the business world. Now, all those words just basically sounds like, you know, we're kind of pumping up mathematics. And the thing is, you know, it doesn't need to be introduced, right? Everybody knows math, but the thing is, everybody knows math in a proud ignorance sort of way, right? How many times in your life have you heard somebody say, or you might have said, "Oh, it's okay, I suck at math," right? Because there's a proud ignorance to it, right? But never, not never, but hardly do you ever hear somebody say, "Yeah, I'm good at math. Let's see what we got here," okay? And the reason why math is taught and here at the college level, I mean, yeah, you're probably not going to use a lot of this, but the thing is, as mentioned, and as you'll see in this particular section, mathematics, the thought processes behind mathematics is what helps you, you know, be intellectual, be, quote, smart, right? Your other courses, you memorize words, right? You memorize words, you might memorize dates in history class or something, but you memorize. In mathematics, memorization can only get you so far, right? You have to actually think your way through some problems, and we'll see that as we progress through this section. Right? Let's see.
Professor?
Yes. Yes.
When we have our math tests, are they just about math, or are we going to be testing on what the textbook is saying? Like, for instance,
You're going to be tested on both, but yeah, I mean, you're going to be tested on what we go over. No. All right. Anyways, so let's scroll on down here to inductive reasoning. Again, let's see, why is it not showing all the way? Maybe I need to make it smaller because I should be able to see the example down there. Or is it cut off? One moment, hang on, let's see. Okay, I think it just cuts off. Right. I've been having this problem with this tablet, not going all the way down in pages. Okay, so this is going to be awkward. Right, so I'm going to have to try something a little bit different in this particular course. It might be a little weird, but we'll try it. Anyways, first thing we're going to start off with is inductive reasoning. And I'm just going to try and go back to tablet mode. I don't know why this textbook doesn't show up all the way. Current page. Okay, I actually should have. Let's go back a second. Right. So starting off, we're going to talk about inductive reasoning. All right. So mathematics involves the study of patterns. In everyday life, we frequently rely on patterns and routines to draw conclusions. Here's an example. The last 6 times I went to the beach, the traffic was light on Wednesdays and heavy on Sundays. My conclusion is that weekdays have lighter traffic than weekends. All right. You all have done that. Everybody has made a general statement based off of a previous experience. Right. This type of reasoning is referred to as inductive reasoning or induction. Right? So the definition of inductive reasoning is the process of arriving at a general conclusion based on observation of specific examples. Okay, we're going to be talking about inductive reasoning and deductive reasoning today. So pay close attention to the words about this one, right? So we arrive at a general conclusion based off of specific examples. Although inductive reasoning is a powerful method of drawing conclusions, we can never be absolutely certain that these conclusions are true. For this reason, the conclusions are called conjectures, hypotheses, or educated guesses. A strong inductive argument does not guarantee the truth of the conclusion, but rather provides strong support for the conclusion. If there is just one case for which a conjecture does not hold, then the conjecture is false. Okay, so let's look at the example, and it's not scrolling. Dadgummit. Maybe I can minimize it a little bit. That's a little too small, isn't it? Okay, so we're just going to try this. I'm going to take it out of tablet mode, but I don't want to continue to take it out of tablet mode. Right, so this is something, I mean, there's not much computation here, right? So example 1, the 10 symbols that we use to write numbers, namely 0 through 9, they're called digits. In each example shown below, the sum of 2-digit numbers is a 3-digit number, right? So, I mean, that makes sense, right? 47 plus 73 is indeed 120, and it is a 3-digit number. 56 plus 46 is indeed a 3-digit number, right? Can we say that the sum of two-digit numbers is always 3 digits? No, of course not, right? So this reads, find a counterexample. I mean, 9 and 7, right? Well, I'm sorry, 2-digit numbers. 12 and 13, right? 12 and 13 is equal to 25, which is a 2-digit number. So obviously, this is not a true statement. Okay, so yeah, the sum of 2-digit numbers is a 3-digit number. That is a false statement. That's how we found counterexamples to these inductive reasoning problems. Okay, and of course, the solution in the textbook, it says 56 plus 93 is 99. I'm sorry, 56 plus 43 is 99. Okay, and then of course, these checkpoints, but this is a pretty fun checkpoint, right? It's pretty easy. Find a counterexample to show that the statement that product of two-digit numbers is a three-digit number. Well, I mean, again, is that a true statement or is it not? And I'll let you decide on that one. Okay, so let's see. Let's snip this as well. No, that's a bad snip job. Let's try that again. Alrighty, so here are two examples of inductive reasoning. So a strong inductive argument. In a random sample of 380,000 freshmen at 722 four-year colleges, 25% said they frequently came to class without completing readings or assignments. We can conclude that there is a 95% probability that between 24.84% and 25.15% of all college freshmen frequently came to class unprepared. All right, that's a strong inductive argument because we have a sample size of 380,000 freshmen, and 25% of them said that they come to class without reading assignments. So we can reasonably conclude that 95% of students, there's 95% probability that between 24.8 and 25.1% of all college freshmen came to class unprepared. Right, that's a reasonable conclusion that we can draw from the data of 380,000 freshmen. Okay. Now, a weak argument. Neither my dad nor my boyfriend has ever cried in front of me. Therefore, men have difficulty expressing their feelings. Okay, so in this world, right, I would assume the two prominent male figures in this particular person's life has never cried. Okay, but you cannot draw that conclusion just from those two people, can you? Right? So that would be a weak inductive argument. Right? So inductive reasoning is extremely important to mathematicians. Discovery in mathematics often begins with an examination of individual cases to reveal patterns about numbers. And we'll get into these patterns here in a moment, right now. Right? So, alrighty, so we're going to identify some patterns. Right? These are just obviously low number patterns, but it does stimulate a part of your brain where you use your reasoning and problem solving skills. Okay, so we'll start with example 2, number 8. Let's see. That's probably super loud on the YouTube video. Me transferring back and forth, but it is what it is. All right, so A. All right, so we have 3, 12, 21, 30, 39. Okay, now all of you, or at least probably most of you, can immediately see the pattern, right? From 3 to 12, okay, well that's 9, right? From 12 to 21, that's also 9. From 21 to 30, that's 9, and from 30 to 39, that's 9, right? So it looks like in each case we add 9 to the term to get the next term, right? So that was a pretty easy one, right? Let's try B. Okay. Well, B, I mean, it appears, if we start adding, it gets pretty big pretty fast, right? But we know the relationship between 3 and 12, right? The relationship between 3 and 12 appears to be multiplied by 4, right? 12 is indeed 4 times larger than 3. Well, it appears 48 is 4 times larger than 12. Okay, and then we know that 192 is 4 times larger than 98 because 98 times 2 is, 48 times 2 is 96, and 96 times 2 is 194. So 192. Sorry about that. So we can see that everything seems to be 4 times greater, right? Well, maybe you are unsure, so you're going to put into your calculator 768 divided by 192, and we should get 4. Right? So it appears that these numbers are just being, you take the number and you multiply by 4, right? So it appears to be let's not do red. and honestly I should probably be a lot more specific with A as well. It appears to be some sort of n, n plus 9, right? And in B it appears to be some sort of n times 4, right? The number times 4. All right, what about C? Okay, well, we go 3, 4, 6, 9, 13, 18. Okay, so again, the pattern here might not be obvious to some of you, but then it might be obvious to somebody else, right? It appears that we are adding the next greatest integer, right? So what I mean by that is from 3 to 4, we're adding 1. From 4 to 6, we're adding 2. From 6 to 9, we're adding 3. From 9 to 13, we're adding 4. From 13 to 18, we're adding 5. Okay, and honestly, maybe I'm jumping a little bit ahead of myself. I probably, if I would have read the problem, it would have made it easier, right? Plus 9 is 48. I'm just going to get my calculator. 60 times 72. All right, all I did was take 768 multiplied by 4. C, all right, so if from 13 to 18 is we're adding 5, then from 18 to 24 we'll be adding 6. Right? We're just adding 1 to each number, right? All right, D, all right, so 3, the relationship between 6 and 3, it looks like, 6 is, it's 3 plus 3. Okay, that makes sense, right? But then from 6 to 18, if we did 6 plus 6, that's 12. Okay, so that's not the pattern, right? What's the relationship between them? Or, is it doubled? That's kind of what we just did, but no. It appears 6 is 2 times 3, but it appears 18 is 3 times 6. And then it appears 36 is 2 times 18, and then it appears 108 is 3 times 36. Okay, so we can, I'm sorry, 2 times. So we can reasonably assume that it looks like it's times 2 times 3 times 2 times 3, right? So what we're going to do is we're going to multiply 216 times 3 to get to 648. Okay. And I've been having issues with my stylus today. It's not writing too well. But there we use some inductive reasoning to figure out the next number in the pattern. And I think that's fun. That seems like a nice, fun exercise. Dang it. I wish I could figure this out on the fly, why we can't scroll all the way down when I'm not in tablet, or when I am in tablet mode. Alrighty. So that's basically what we just did, just a thought process there. All right, so this reads, in our next example, the patterns are a bit more complex. Ooh, now this is going to be fun. So some more complex examples. Now, obviously, I know the patterns, right? Because I come to class prepared. Right. So I'm trying to tell you how my thought process was when I first was introduced to the problem. So there's that. So if I seem kind of, I wouldn't say fake, but kind of not genuine, that's honestly why. Sorry. So let's go ahead and figure out this, identify the next number in the pattern, right? So A, I mean, I can tell right away A is what's called the Fibonacci sequence. I can't write like that. Okay, so I can tell right away A is a Fibonacci sequence because it's actually a very prominent sequence in mathematics. Okay, but anyways, let's proceed and figure it out, right? So it looks like we start with a 1, good, right? And then it looks like 1 plus 1 would be 2, right? Or how about this? And we start with a 1, and that 1 plus 0 is going to be we're going everywhere here. Is going to be 1. Right. Well, then we add those two digits, these two together, and we get 1 plus 1, which is equal to 2. And then we add 1 and 2 together to get 3. We add 2 and 3 together to get 5. We get 3 and 5 together to get 8. And then hopefully you can see the pattern, okay? So this means that it looks like we would do 13 and 21 together to get to 34. Okay. Again, this sequence is actually a very famous sequence. It's called the Fibonacci sequence. And it's very famous because you see the sequence arise everywhere. Okay, now I will admit, if you're looking for something hard enough, you can find it. But the Fibonacci sequence, and especially the golden ratio, which we can see in the Fibonacci sequence, we see that the golden ratio and the Fibonacci sequence arises in finances, in the stock market, in nature, and I think it's pretty cool. All right, now B, I'll admit, B was pretty tough for me. Okay, I've obviously done a lot of these in my life, so I knew what I was looking for, and I thought that this kind of pattern would show up in example 2, but it didn't. But it's not necessarily simple, but once you see an example like this, you'll understand that, oh, it's actually pretty easy, right? So let's go ahead and start with it, right? So what's the relationship between 23 and 54? Well, I mean, it's not twice that, it's not 3 times that. Okay, so it would be, it looks like 23 plus 31 is equal to 54, right? But then what's the relationship between 95 and 54? Okay, well, that's 41, okay? So what looks like we're getting a pattern here. Cool. So now what's the relationship between 95 and 146? Well, that's 51. And then the pattern just disappears, right? Because we go from 146 down to 117. So that's not it, right? So what could the pattern be? Okay, so now this is where, like I said, seeing these particular problems is what you'll get better at it. And again, some of you might already have it, right? So here's another way to look at the pattern. Okay, well, kind of how the Fibonacci sequence, how we added the numbers together, right? We did 2 and 3 is 5, 3 and 5 is 8. Let's do this. Well, 2 plus 3 in this particular problem, okay, is 5. Okay, but what about that 4? Where does that 4 come from? Okay, well, it looks like it's 1 more than my 3, so there's that, right? The 3 on the 23. Let's make this larger so I can mess with it a little bit more. Okay, we're gonna make it a little bit larger. Okay, so the relationship here. So I know that 2 and 3, so 2 plus 3 is equal to 5, okay, which is this number. I also know that 4 is 1 more than 3, and I notice that 5 is 1 more than 4, 6 is 1 more than 5, and it looks like a good pattern right there, doesn't it? Right? It looks like we take that last digit and go up 1 unit. Okay. Well, simultaneously, it looks like I said, 2 plus 3 is 5. Well, 5 plus 4 looks like it's 9. 9 plus 5 looks like it's 14. Okay. Well, now 1 plus 4 plus 6, right? That is 11. And then, of course, we said we added the 1 to the 6 there. And then 1 plus 1 plus 7 is equal to 9. And then we go up 1 there. Okay. So that appears to be the sequence there, right? So with that said, what we're going to do is we're going to take the 9 plus 8. Okay, well, 9 plus 8 is equal to 17. Okay, and then we go, we take this number here and we go up 1, right? So we go from 8 to 9. So we could reasonably assume that 179 is the next number in that sequence, right? Now, in my opinion, this is a lot more fun than mindlessly factoring your brains out. So, I don't know, maybe it's just me. It's a lot more fun to me. Hopefully it is to you too. Y'all picked a great class to sign up for. Okay. 179, that's our thing. Okay. This great question here, it says, can a list of numbers have more than one pattern? Corey? Check that out. Obviously, there would be more than one pattern, okay? But check that out, read that. There's also maybe it's not, but there's also a thought process of No, let's save that for later. Alrighty, so let's. Where's my snip? There it is. Alrighty, so mathematics is more than recognizing number patterns. It is about the patterns that arise in the world around us. For example, by describing patterns formed by various kinds of knots, mathematicians are helping scientists investigate the naughty shapes and patterns of viruses. One of the weapons used against viruses is based on recognizing visual patterns in the possible ways that knots can be tied. Right? So this particular example, which, by the way, this is kind of like, our IQ test, right? What is the next in the pattern? Okay, well, let's examine this. It looks like we're going from circle to square, from circle to square. Okay, so we can reasonably assume that the fifth item in that pattern will be a circle. Okay, well, now let's look at the patterns of the circles. Put my screen down. Okay, so we can reasonably assume it's going to be a circle. It's a pretty good circle. All right, looking at the patterns, it looks like we have 3 on the left, and they have 1 on the right, and then 2 on the bottom. Okay, what looks like what happens here is that the next circle, it looks like everything's flipped, right? Instead of 3 dots right here on the left side, there's 3 dots on the right side. Instead of 1 dot here, it's over here, and then same thing with 2 dots there. Okay, so it can be reasonably assumed that yes, it's just going to be a circle, but also that probably the pattern might, looks like the pattern might just repeat itself. Those aren't good dots. Might be better. Okay, that, and then good. And that. Okay, so we can reasonably assume that it appears that the patterns repeat itself. Go from circle, square, and then it goes to the dots also repeat themselves. All right, that was inductive reasoning. Okay, that's. All right, sorry guys, I obviously didn't rehearse a lecture. I did not know that it would not be able to scroll with just touching the screen. Anyways, all right, so now that was inductive reasoning, okay? Now we're going to talk about inductive reasoning, all right? So, I'm sorry, deductive reasoning, sorry. Let's move this up. So real quick, let's go back and define what inductive reasoning was. Okay, so inductive reasoning was the process of arriving at a general conclusion based on observation of specific examples. Okay, so just a general idea of what could be, right? That person that has never seen their boyfriend or their father cry, right? It could be induced that yes, maybe that males don't cry, but we obviously know that that is false. But that is an inductive reasoning type. Okay. Deductive reasoning. Well, let's just start from top. I was going to read straight for definition, but let's start up here. So deductive reasoning. We use inductive reasoning in everyday life. Many of the conjectures that come from this kind of thinking seem highly likely, although we can never be absolutely certain that they are true. Another method of reasoning called deductive reasoning or deduction can be used to prove that some conjectures are true. Okay, so deductive reasoning is the process of proving a specific conclusion from one or more general statements. A conclusion that is proved to be true by deductive reasoning is called a theorem, and that is the crux of mathematics, right? The entirety of mathematics is built upon definitions and theorems. All right. So let's look at, well, we're not done here. Okay, so deductive reasoning allows us to draw a specific conclusion from one or more general statements. Two examples of deductive reasoning are shown below. All Right? Notice that in both situations, the general statements from which the conclusion is drawn is implied rather than stated. Okay, so here's our everyday statement. So if one player says to another in Scrabble, you have to remove those 5 letters. You can't use Texas as a word. Okay, so our statement here is that all proper names are prohibited in Scrabble. Okay, well, since Texas is a proper name, therefore Texas is prohibited in Scrabble. Right? That is our deductive reasoning. Right? And again, you've done this many times in your life. Right? There's nothing new for you. Advice to college freshmen on choosing classes. Okay, so here's advice on choosing classes, which, by the way, I think is spot on. Never sign up for a 7 a.m. class. Yes, you did. Yes, you did it in high school, right? You had class. I don't know if you had class at 7 a.m. I don't know. That sounds awful. But anyways, yes, you did it when you were in high school. But your mother was always there to keep waking you up. And if by some miracle you do make it to an early class, you will sleep through the lecture when you get there. Guys, I think that's actually really good sound advice. Okay, but it's not necessarily a rock solid conclusion, right? So the statement is all people need to sleep at 7 a.m. Okay, the statement alone is false, right? I mean, there are plenty of people that do not need to sleep at 7 a.m. Right? But anyway, so the conclusion is you sign up for a class at 7 a.m. Therefore, you'll sleep through the lecture or not even make it to class. Okay, so what this is saying is I mean, based upon the general opening statement, right? If your opening statement is false, then your conclusion is also going to be false, right? Let's think about another one. So like something like all ogres are green. Okay, so are all ogres green? I've used an example in class, and I hear many students say, yeah, of course all ogres are green. But are they? Have you ever seen a real life ogre? Right? I mean, jokes aside, ogres don't exist. Ogres are in fairy tales. Okay, so if your general statement is false, then it doesn't matter what conclusion you reach. Your general statement is not a true statement to begin with. Okay, let's snip this real quick before we talk about anything. Okay, so this reads a brief review. Right. So some of you may already be on top of this, but as we know, a sum is the result of addition. The difference is the result of subtraction. The product is the result of multiplication, and a quotient is the result of division. Okay. So let's. What I'm going to do, instead of picking my own numbers, I'm going to just follow along with the numbers that they picked instead of doing the math behind this. But B is really the important thing, so we'll definitely discuss B. But for the moment, I'm going to cheat, and let's see. Let's take this one out. Okay. So starting from the top, right? So example 5 reads, consider the following procedure. Right? So select any number, up here, select any number, multiply the number by 6, add 8 to the product, divide this sum by 2, and then subtract 4 from the quotient. Okay, so A reads, repeat this procedure for at least 4 different numbers. Write a conjecture that relates this result of the process to the original number. Okay, and B, we'll do B off to the side here. Okay, now in the textbook chooses 4, 7, 11, and 100. Okay, so the procedure is we select the number, that's number 1. The first step we're going to do is multiply the number by 6. Okay, so in each of these steps we see that we're multiplying by 6, right? 4 times 6 is 24, 7 times 6 is 42, so on and so forth. Next we're going to add 8 to the product, so we see that we're adding 8 to the product, right? Then we're going to divide this sum by 2, okay? So we're going to divide it by 2. So 32 divided by 2, 50 divided by 2, 74 divided by 2, 608 divided by 2. And then we're going to subtract 4 from the quotient. Okay, so then we're going to take 4 away from the quotient. Right? So in this particular case, we start with a 4. We start with a 4, and we get a 12. We start with 7, we get a 21. We start with an 11, we get a 33. We start with 100, and we get a 300. Of course, that can be seen down here in this table. Okay. So we see that our original number selected is 4, 7, 11, 100, and then the result of the process is 12, 21, 33, 300. Okay, so we see that it appears, the pattern seems to be that in the end, after we do these steps, that we are essentially multiplying our original number by 3. Okay, this is inductive reasoning, right? We followed the directions, and for following the directions, seeing what the resulting number is, and comparing it to my original number, I can reasonably say that, okay, so this process multiplies the number by 300, or I'm sorry, by 3. Okay, that's inductive. Now we're going to talk about deductive. Okay, deductive reasoning is a more concrete result. Okay, so let's see this concrete result. So B, in this particular case, it says use the variable n to represent the original number, and then use deductive reasoning to prove the conjecture. Okay, so let's do that. Let's put this over here. We're going to say B. All right, so we're going to start with the number, or with the letter n. Okay, so n, that's our number. We're going to multiply this number by 6. Okay, so n times 6. Okay, we can rewrite that simply as 6n, right? Right, that's the first step. We're going to add 8 to the product. Okay, so we're going to add 8 to 6n, so it's just going to be 6n plus 8. Okay, and then we're going to divide this sum by 2. Okay, so we're going to take 6n plus 8 and divide it by 2. So let's actually denote first step, second step, and then the third step is 6n plus 8 divided by 2. Okay, so 6n plus 8 divided by 2 looks like that. We know from our algebra that we know that we can essentially split those two up into a fraction, right? So it would turn into 6n over 2 plus 8 over 2, correct? Okay, well 6n divided by 2, well that just becomes 3n. Okay, so that just becomes 3n. And then 8 divided by 2, that just becomes 4. So 3n plus 4. Okay. And then the last step is to subtract 4 from that quotient. Okay. So my last step is to take 3n plus 4 and then subtract 4. Well, that seems pretty obvious now, doesn't it? 3n plus 4 minus 4 is just simply going to be 3n. Okay. So through deductive reasoning, we have proven our conjecture that we arrived at through inductive reasoning. Okay, you take any number n and you multiply it by 3, and that's what happens after you complete this procedure. And again, like I said, we figured that out here, right? We figured that out here, but we can't positively say that it's a true statement until we can prove it deductively through here. Okay, now I say that very loosely, I suppose, because there is a procedure in mathematics called proof by induction, but that's I don't know if I actually prove by induction in this class, actually. I haven't taught this class, so maybe we do proof by inductions, but as far as I know, maybe, I assume maybe we don't, but regardless, we just proved that that procedure does indeed produce the result that we saw through our inductive reasoning. Is that the end of the section? Shoot, that was. Okay. Well, that was fast. Okay, well that concludes chapter 7, section 1.